to 1500.
Tonesis Carter Williams.
Okay, hi. Thank you for coming to my presentation. My presentation is called Remote Sensing Sediment, Analyzing How Sediment Changes Seasonally in Coastlands of Southeastern United States. My name is Carter Williams, and my mentor is geobiologist Dr. Mariotti. This summer has been an exciting opportunity for me to explore a research field that I was previously entirely unfamiliar with, which is sedimentology. So let's talk a little bit about the importance of the Louisiana wetlands. So the Louisiana wetlands provide many important ecological services, including but not limited to fisheries production, resting areas for migratory species, carbon storage, and water filtration. So though humans rarely do it on purpose, sometimes our actions can inadvertently harm the wildlife and forestry of these areas. So actions made in order to protect the human residents of Louisiana have sometimes resulted in endangering species of animals, lessening water filtration, increased erosion, and other detriments to the wetlands. So in order for us to make sure that we are not endangering any part of the wildlife, we need to take investigative action to understand the environment around us. So what tool can we use to monitor the wetlands? Well, you can probably guess based off the title, but remote sensing. So that would be a super useful for monitoring the environment at a macroscopic scale. So what exactly is remote sensing? For those of you who don't know, remote sensing is the scanning of the Earth by satellite or high-flying aircraft in order to obtain information about it. So naturally, satellites are very expensive and difficult to launch, but luckily there is a free resource for scientists out there to access thousands of satellite images. And that resource is called Google Earth Engine. Google Earth Engine combines a multi-petabyte catalog of satellite imagery and geospatial data sets with planetary scale analysis capabilities and makes it available for scientists, researchers, and developers to detect changes, map trends, and quantify differences on the Earth's surface. That is a quote that is taken from their site. This tool would be a perfect fit for geobiologists to analyze the Louisiana wetlands. So let's just take a little quick look at the overview of the process of which I'm doing. So first I run a program that is a combination of both Dr. Mariotti's code and my code that is on Google Earth Engine. Then this code takes data from MODIS, which is the Moderate Resolution Imaging Spectroradiometer, which is aboard the Terra satellite, also known as the EOS AM1, and the Aqua satellite, or the EOS PM1, which is really, really cool. And then filters that data based off of time taken, the quality of the pixel, and whether that pixel is relevant. So to see if that pixel is actually relevant, if that is actually on water instead of land, because we're only interested in sediment in the water in this case, I actually take landmass data from another satellite called the Landsat 8, which is also really cool. So next, that data is sorted into a high tide data set and a low tide data set. And finally, that data is exported into a Google Drive where I can then access it in Google Collaboratory to visualize. So Google Collaboratory in this case is kind of serving as the meeting point for all the data that I collect, which is the satellite data, the tidal data, and the streamflow data. So the data that I'm collecting isn't actually in Louisiana in this case. Naturally, Louisiana isn't the only state that would benefit from using satellite imagery and remote sensing. So a lot of tools and techniques that are used to better our understanding of the wetlands can also be used to benefit other coastal states. My mentor, Dr. Mariotti, has specifically tasked me with gathering data of the Altamaha River in southeastern Georgia. So it can be very similar to rivers in Louisiana in some ways. So collecting data about it could prove to be useful in the future. Using Google Earth Engine, let's take a look at the mouth of the Altamaha River. We can organize the pictures based off of tidal prediction data taken from the National Oceanic and Atmospheric Administration, or NOAA for short, so that the pictures are compiled into two separate categories of high tide and low tide. So if we take these two resources and combine them, we'll see what happens. And we get a chart that looks, or a figure that looks a little like this. So here are the average sediment levels for each month of 2019 at both high tide and low tide. So it's kind of hard to see from this distance, but you can make out that low tide has a considerable amount of sediment more than high tide. So let's zoom in just a little bit. Right, and so you can see all, right, there's a considerable difference in low tide. There's a lot higher sediment levels. And this makes sense. If you were to pour water into a glass halfway filled with sand, the sand would be disturbed by the motion of the water and be more distributed through the glass. But if the water were drained, if the water were drained, the sand would naturally pile up back at the bottom of the glass. So if we were to take this analysis even further and compare the sediment rates during high and low tide with stream flow data taken from the United States Geological Survey at Doctortown, Georgia, we could perhaps see some interesting things. It would be interesting in particular to see how much the stream flow taken a couple miles north of the river mouth affects the levels of sediment. So you can see right here, you can see that little red marker is Doctortown and the mouth is right here. All right. So here's the chart of the average sediment levels per month since 2003. The average for high tide is the blue line, the average for low tide is the orange line, and the average for the river stream flow is the dotted black line. So as we can see, there are a lot of correlations between the river discharge and the sediment levels. You can see one right at 2016, there's one, 2020, there's a big one right around 2010, and another one around 2009. So a lot of correlations that can be seen. And here we have another comparison that's further upstream near Broadfield, Georgia. There's only one line plotted for the average monthly sediment because tide is understandably negligible this far upriver, doesn't super matter in this case. But again, we can see many correlations between the stream flow and the average levels of sediment. So thank you so much. That was my presentation.
Questions?
Yeah, I got one. That was an interesting talk, Carter. I was curious how you correlated, I guess, the turbidity or the color of the pixel with suspended sediment concentration in the water. How did you establish that relationship?
So I think the satellite kind of mostly does it for us, but if you're specifically asking about just the way that the color is working, that is just something that I took from Matplotlib. It's just the and it's also what Dr. Mariotti uses, so I just kind of take that advice from him.
Okay.
Yeah.
Another quick question. So the sediment level and your satellite images, are they open source? Do you have any source so we can look it up? Data?
I'm so sorry.
Yeah, so data collection. Yeah, so for data collection in your chart and visualization, and those satellite images open source? Is there any source that we can look it up?
Yeah, so right, Google Earth Engine is open source. I had to apply for it, so it would take a day, but you know, I'm actually not sure. I'm sure that there's got to be a place where it's already visualized out there, but in this case, right, I had to write some code to actually get those images. But Google Earth Engine like has that free for everybody. You just have to apply, which is super fun.
I mean, to the best of my knowledge, all data from NOAA is, I mean, you can access it.
Right.
I suppose from the geological, whatever, I forgot, I suppose that also public, but I'm not that familiar how to access the geological, what is called, reserve or?
Sorry, my internet's a little strange right now, so I can't quite hear as well, but was there a question in there?
No.
Oh, okay.
The website's usgs.gov, and it's all open source.
Okay, and you can access it too. I mean, the data. Okay, no, I'm not that familiar with that, but good to know. Okay, great. There are no more questions. Thank you, Carter. So next